first of all, I would like to join the other speakers in thanking the organizers. And if any of you has tried to organize anything these days, you know it's really an exercise in frustration. So I mean, I'm really impressed that we made it here. So today I'm going to tell you something related to some work that we've been doing for a number of years now. And there's a bunch of references there, but actually what I would really like to talk about is something that hopefully you will see on the archive next week. And there's a bunch of references, which means there's also a bunch of collaborators, and some of them are in the room. In the room, actually, there are also people that have made very important contributions to this field, in particular Gabriel that is sitting there. I will not cite any work at all, so don't get offended. But in any case, I wanted to show you a bit who are my friends and show you that we pretty much delocalized, even though in this moment, I believe half of the people are sitting in this room. So what is all this story about? Well, mainly we're interested in conformal field theories, right? So I shouldn't tell you why we're interested in conformal field theory. It's obvious to everyone. The point is, you study QFT, sooner or later, you're going to hit a conformal field theory, either because you're looking at the phase diagram and generically is what you find at the end of the flow, either because you do condensed matter and then you're interested in critical phenomena, either because you're interested in quantum gravity, and that's conformal field theory is the only way that we have to reach quantum gravity as of now, either because you're string theorist and string theory only works because it's secretly 2D CFT, right? Now, the point is the following. It's so interesting, it's so beautiful, but it's really complicated in general. And the reason why it's really complicated is that by construction, there are no scales. And so generically, at least, you don't expect a CFT to have nice parameters that can be dialed to some simplifying limit. Okay, so which means that generically, you don't expect all the perturbative machinery to work for a generic CFT. Now, you can do things, of course, you can do bootstrap, for example, you can use symmetries in general, but our point, a little observation, was that if your system is a CFT and has also a symmetry, you can decompose its Hilbert space essentially in sectors of fixed charge, and maybe there are sectors of this theory where the computations of the CFT data simplifies. Okay, so if there is really one message that I'd like you to bring home today, is the fact that what you can do, at least generically, is that you can study subsectors of the theory for fixed values of the charge, and if you're lucky enough, in each of these subsector, Q will become the controlling parameter of some sort of perturbative expansion. Okay, so okay, the cute words, but concretely, what can we do? Okay, so one of the first predictions that we made was about the conformal dimension or the lowest operator of fixed charge in the ON vector model in 3 dimensions. Okay, so this is one of the first CFTs that everybody encounters already when studying, and we know that there's a fixed point, but it doesn't mean that it's easy to compute. Okay, in fact, generically, you can do bootstrap, you can do numerics, you can do lattice. Actually, many of the things I will be hiding today are the things that Masahiro spoke about, because there's going to be a lot of lattice and sign problem that was brilliantly solved in this case by my collaborators. And anyway, the point is you can compute conformal dimensions, some approximation, but generically you miss something simple, some simple formula if you want for these dimensions, and that's what we offered. So what we derived was a simple formula for the conformal dimension or the lowest operator of given charge. And as you see, this thing goes like q to the 3/2, then there is a q to the 1/2 term, and there are 2 coefficients, c3/2 and c1/2, that you will see very soon why they are beyond reach of our approach directly. And then there's a little number here, which is universal, and turns out to be the first of a series of universal numbers that appear in conformal field theories. And again, Gabriel found other numbers like that, and it looks like there is a little bit more structure that we still have to understand. So what did we do after we got this result here? Well, the first reaction was, this is too simple to be true, so we need to see where it's valid. So I keep saying large charge, but I didn't say how large. What does large mean? 10, 100, 1 million? That we didn't know. And we have to find another way of computing the same things, just to verify if our conjecture was good or not, well, if our construction was working, actually. So what we did is that we went to the lattice, and we had to find lattice people that were good enough to try to tackle this problem, which is actually difficult, just numerically is a complicated thing. So what they did is that they did actually find a nice way of contouring the sign problem, like Masahiro was telling us before, and they actually computed the conformal dimension for the O2 model in 3 dimensions. So that's the O2 model. So n is 2, so you cannot do in large n. The dimensions are 3, so epsilon would be 1, 4 minus epsilon. You cannot do like that. You really have to do it on the lattice, okay? And what they found are all these points here. This is really the conformal dimension of the lowest operator for given charge Q. Charge is, of course, quantized. And here, before we're talking about error bars, you don't see the error bars because the error bars are less than 1 pixel, okay? So there are error bars, they're just invisible. And the continuous line, on the other hand, is the prediction we made before, where we had to fit 2 parameters. Okay, so there were these 2 parameters in the formula before that are not computed by our theory. We have to fit them. You can pick any 2 points, as you can imagine, but this thing is predictive. You give me 2 points, I give you 11. Okay. And when we saw this thing, actually, this was really a game changer for us, because all of a sudden it looked like our construction, which was based on some assumptions here and there, actually was working. It was really reproducing the physics of the, at least the O2 vector model. So how does this stuff work? Well, it's based on constructing effective field theories, right? So how do you explain effective field theories to your students usually? What you say is that you have your theory, you set a cutoff, you distinguish between high energy and low energy degrees of freedom, you integrate out the high frequencies and you get an effective action. And when you say that, everybody goes like, oh, yes, yes, of course, yeah, sure. And you know, you feel bad yourself because you know that you'll be lying, right? Because this is not the way to do things. You wish you could, but this is equivalent to solving the theory, which you can't. What you really do is something else. What you actually do when you want to construct an effective field theory is that you try to understand what are the scales of your problem, okay? It's the same story as in chiral symmetry breaking. So what are the scales of this problem, since it's a CFT? There are no scales. Well, depends. One thing you can do is that you can put your system in a box, okay? Now, what does it mean exactly putting a CFT in a box is a bit of a tricky thing since there's Weyl invariance, but let me go on with that for the moment. And then you need another scale. And this other scale is given by fixing the charge. You fix the charge, this gives you charge density. So now your problem has 2 scales. One is the inverse, well, one is the size of the box, the other is the charge density. And what you can try to do, and what we actually managed to do, was to write an effective action with typical scales, with a cutoff lambda that sits in between these 2 scales, which both of them are very far from the UV scale where the physics is different. So the idea is that if you manage to write an effective theory with lambda in between these 2 values, naturally your system will be weakly coupled and controlled by the ratio. The perturbative parameter is the ratio between this scale here and this scale there. So as long as Q is very, very large, you can hope that you have enough perturbative control that you can say things about this regime. Okay. Now, this, of course, doesn't fit at all with what we see here. In fact, when you seen the picture before, you should have been very worried because, again, I kept saying large charge, but then this thing seems to be working unexpectedly well also down here. So if you want to talk about that, I'll be here all day. I will not be concentrating on this. What we can say now that we couldn't say a couple of years ago is that at least in a case where everything is controllable, namely in large N, we can explain where this comes from using resurgence. So there's Nicola is sitting down in the back. He's an expert in resurgence. And together, we managed to find a way of understanding why this thing keeps working. The secret is these are asymptotic expansions, actually, that we're writing. And somehow they work better. As usual, they work better than they should. But anyway, this is not what I want to talk about today. Today, I will very quickly review how to construct the effective field theory for the O2 model. But I will then concentrate more on what happens in large N. Why large N? Because in large N, we have enough control over the theory that we can go beyond, well, we can prove that what we construct on the FT works, and we can say more things about it. And then I will actually change my point of view in the sense that instead of trying to use large N to verify things that we find in the effective field theory, what I will do is that use the charge inside large N to extract more information about the physics at large N. Okay. So this is, as I said, unpublished work, and this hopefully should be on the archive next week. But yes, go.
Thank you. Can you just say what the similarities and differences are with large spin?
Oh my God, no.
Okay.
Yes, no, yes, of course. It is long. And these are things, I think it's fair to say that we don't understand it well enough, just to say exactly why the things are different and how much the things are different. What is interesting is that you can study intermediate regimes where you see, you switch on both the charge and the spin. And then you see in different regimes how things change and how the two things can be related and how to use semi-classics in one case and how you use semi-classics in the other. As I said, the philosophy is similar, but you shouldn't ask the question to me, you should ask a question to Gabriel, who's the actual expert. So he's just sitting 3 meters from you. Okay, so this was the end of my introduction. And from now on, I'll be a little bit more explicit. I'll show you more formulas and try to convince you that this thing is actually something you can do calculations with. But again, the main idea is that we need to use the symmetry. That's the whole point. Good. So what is the simplest example of theory where all of this machinery is useful is the O2 vector model. And the O2 vector model, you know, it's just Wilson-Fisher fixed points. Again, the first thing that you encounter in the books, and it's the non-trivial fixed point of phi to the fourth. Okay, so it is something strongly coupled, and we said before we really don't know how to deal with it well because it's not large N, it's not small epsilon. You can do it on the lattice as we did. You can do it in Bootstrap for some sectors, but you still have to figure out what to do. Okay, so what was our observation? Our observation is that, at least in this case, if we consider a subsector of fixed charge Q, then everything works as if your classical solution, a fixed charge, breaks spontaneously the O2 or the U1 symmetry. So what you expect is that the low energy physics is described by a Goldstone boson. That's it. Now, how do you write the action for this Goldstone boson? You think, fine, I have a field chi. I start writing the simplest action that is possible, right? So two derivatives, and then things start to be a little bit more tricky because chi is a Goldstone, so it's dimensionless. This thing is in 3 dimensions. You have to get to dimension 3, so you need to put an f pi, you know, like chiral symmetry breaking, but f pi has dimension 1. Also, as I said, I want to put my system in the box. It will be more obvious why in a couple of slides. So I can also put a constant, sort of cosmological constant thing, which has dimension 3. Well, c to the 3 has dimension 3. But clearly, this is wrong, right? We want to describe a system that is a conformal field theory, so it's approximately scale invariant, so there's no way you have dimensionful couplings in this thing, right? But we know what to do with it. How do we turn this into something useful? Well, how do we turn it into something which is conformal invariant? We add the dilaton. We just dress everything up with a dilaton. We add a field sigma that transforms non-linearly under Vairé scaling. And then adding the right powers of sigma, you can write an action, which is this thing here, which is obviously the dressing of the one before plus a kinetic term for the dilaton, which by construction is scale invariant at least. It's Vairé invariant. Now, the way of understanding the fields that appear here is that chi is this Goldstone for the broken U1, and sigma is a massive Goldstone that it describes the broken conformal invariance. Good. So this action is good, but it looks really weird. And you're like, it's a bit unsatisfactory if you look at it. like this. But actually, there's a way to rewrite it, just rewrite this thing in a way that is much nicer. And this is just by observing that if you put together these two goldstones, here, the dilaton and the chi field, and you just exponentiate the thing, you literally rewrite the action before, and that's what you get. It's nothing else than 5 to the 6th. Okay, so here this is just renaming, no more, no less. And what is nice is that I told you before, this had to be the wrong answer because f pi and c are dimension full. What happens is that the f pi and the f and the c, the f that comes with the dilaton and the f pi and the c all combine only into dimensionless parameters. It had to be, in fact, right, by scaling invariance. But it's nice to see it happening. So here's the point, that it turns out that it's convenient to describe the physics of low energy, the low energy physics for this thing in terms of 5 to the 6, roughly speaking, where this phi has not to be confused with the phi in the ultraviolets. There is some very complicated transformation that I have no idea what it is that relates the fields in ultraviolet to this, that is an infrared field. Okay. Now, the fact that it's 5 to the 6 is scary at first because, you know, how do you quantize that thing? In fact, not, it shouldn't, because once you fix the charge, fixing the charge is equivalent to adding a centrifugal term. So what really happens is that your potential is not just the phi to the 6 up here, it's not just 1 over phi squared, which is a centrifugal term, but it's the sum of the two, which means that you'll be describing the theory around the minimum here, where the theory is quadratic and you can quantize and everything is fine. And the cool thing is that the fluctuations around this minimum here are controlled by the inverse charge. That's why you can actually trust a semi-classical calculation done around here. If you want to see the details, you can actually ask for what is a solution of fixed charge, and what you find is that, of course, you're fixing the charge, you're breaking Lorentz invariance, which has a lot of consequences. But in particular, the chi is linear in time, the sigma is a constant in the ground state, and the classical energy of this thing goes like q to the 3/2, q to the 1/2, and so forth and so on. These parameters C3/2, C1/2 are nothing else than the parameters you put before. This you had put by hand from the beginning. You have not computed them, you have no control. And you find them back. But here as dimensionless things that you have to compute, say, on the lattice. Okay? Then you start wondering what happens if I try to quantize this theory. You find that there are things that are universal. In particular, there is a goldstone, that is conformal goldstone, we call it, because it sees still the constraint of scaling invariant, conformal invariance, and so in particular, it does not have speed of light, speed equal to 1, but it's 1 over square root of 2. In general, 1 over square root of d in d dimensions. Plus the dilaton being massive. So remember, we had put it before just to assure conformal invariance, but it was always a little bit to a cheat in a way. So what we can do is that we can integrate it out at the end, and so write a model just for chi, which we could have guessed before from symmetries. And this model just for chi looks a bit funny because it has a kinetic term that goes with 3/2, but again, it's okay. Just like before, adding the centrifugal term means that you're not expanding around 0. Here, you're not expanding this thing around chi equal to 0, but around chi equals mu t. And that's actually a quadratic action in disguise. Okay, good. So why am I insisting about boxes? Because it's a CFT. And in a CFT, we know that we can always turn conformal dimensions on flat space into energies on the cylinder. Which means that if we repeat this computation here on a cylinder, so time cross a sphere, the energies that we find are automatically conformal dimensions of before. The fact that the energy of the ground state before went like q to the 3/2 means that the conformal dimension goes like q to the 3/2. And on top of that, then you can start wondering what are the quantum corrections. These are controlled by 1 over q. The leading one goes like q to the 0, and it's this number here. And this just depends on the square root of 2 of the conformal goldstone. It gives you a number, 0094, which is universal, at least in this universality class. Okay, so what are we seeing? Well, we started from a CFT. There was no mass gap, there are no particles, there's no Lagrangian. It's a CFT. But having picked the sector, the important thing is that the physics is described by a semi-classical configuration plus some massless fluctuations. Okay, and this configuration has no small parameter. Well, even though the system has no small parameters, in this sector we have found the controlling parameter, which is the inverse charge. So we can say things. Now, one thing that you can do is that you can try to repeat the same game, instead that for your two model where you don't know what to do, for another model where you know what to do. Large N, for example, where you can compute things. And then you can ask, is it true that the structure we've seen before is reflected also in systems where I can do computations? So what you do is that instead of taking one field, one complex field, you take n of them. And then you write a partition function, well, a canonical partition function fixing the charge. So you just put deltas inside the trace, where the charge is exactly what you expect. So each of the charges is the thing that rotates a complex field. And again, you repeat this game on the sphere, so that the free energy on the sphere, well, with a porting multiplier and so on, is nothing else than the conformal dimension of the lowest operator. So we really literally computing the same thing as Masahito before. Okay, the only difference will be that instead of computing it, well, instead of being interested in the chemical potential, well, actually no, even Masahito was really interested in a topological charge. This is not the topological charge, but the spirit is the same. Okay, so what you do is that, how do you compute that thing? You see there are deltas here. You rewrite the deltas in terms of integrals, and then what you find is that this partition function you want to write essentially is a Fourier transform of what is here a partition function, a fixed imaginary chemical potential. That's literally the theta of before. Okay, and you want to write this partition function here, this grand canonical partition function, and you see the tricky thing, the slightly tricky thing, is that since you get a chemical potential for the charge, and the charge depends on the momenta, you have to be a little bit careful of how you implement the calculation. Roughly speaking, there are two ways. Either you look at that as a boundary condition when you go around time, or equivalently, you add the flat connection. It's the same thing. So you reabsorb the theta q just by, again, a boundary condition or a flat connection. Let's go the flat connection way. What the only thing that means is that instead of your initial action, the thing to put is just a flat connection in time. Okay. Now, once you do that, you can just take your favorite quantum field theory book and just go on with the standard techniques. So there's a Stratonovich transformation, which roughly speaking means that instead of phi to the fourth, you trade this phi to the fourth for a field, which is this field lambda, which is a collective field, which counts as a phi squared. Okay. And after you've done that, your action becomes quadratic in the phi's. And since it's quadratic in the phi's, you can integrate out the phi's, and you have an effective theory just for lambda. The only slight difference with the usual treatment is that you have to take into account the fact that both the phi's and lambda have a VEV. Okay, and this VEV will be important because that's where the large N physics is all contained. Okay, but in fact, technically everything is very simple. It's just a Gaussian integral that you have to do at this point. And this Gaussian integral you can regularize as you like, but for example, it's nice to regularize it in this case with zeta functions. So the final result is the following: that the free energy here, which is essentially the conformal dimension, can be written as mu times q minus this zeta function here on the surface of your choice, evaluated at a precise point, where mu is the solution to this equation here. Now, this doesn't seem very transparent, but in fact, if you observe that this zeta here and this zeta, well, that zeta in 1/2 is exactly the derivative of zeta in minus 1/2 with respect to mu, you realize that what I've written here is a Legendre transform. And that's no big surprise. This is large N. Large N is the thermodynamic limit. The free energy at fixed charge is the Legendre transform, then the free energy at fixed chemical potential of the grand potential. Okay, so that's exactly what we see here directly. The different, well, the important thing is that everything, all the large N physics is contained in this zeta function. And this zeta function here is something that in the limit of large charge has a very natural expansion, which is Bayes asymptotic expansion. So you just play this game here on the sphere, for example, if you're interested in conformal dimensions, and you can compute all the numbers that you like. In particular, again, I put myself on the sphere, and what I find is that the free energy of fixed charge, which is the same as the conformal dimension of the lowest operator of fixed charge, has this form here. So first of all, it starts with 3/2, as we've seen before, then it goes with 1/2. What we learned new is that now we can compute the coefficients. Before there was C3/2, C1/2 that we had to find from the lattice. Now we can compute them. And one thing that is important is that we know everything about this series. We can prove that this series is now asymptotic. And using resurgence, we can also tell you how the corrections go. And in particular, the corrections go like e to the minus square root of q. That's not what you'd expect generically from a QFT, but that's what you find here. And in particular, you can tell that if you have q over n of order 1, because that's the controlling parameter here, then it's enough to use 2 terms essentially before you hit as an optimal truncation. Okay, so was it worth it?
Previously, you also had a constant term. There's no constant term here?
No, there can't be a constant term because this is a conformal dimension. Well, the free energy of fixed charge, the free energy in the sphere is a conformal dimension. So the free energy in 0 has to be 0 because it's the dimension of the identity. So that tells you, that's actually a very non-trivial check that this is true. The non-zero term that we had before was, we find it also here at subleading in n. So this is large n term, but the zero term, the constant term, has to be universal, cannot depend on n. So since this stuff all comes with an n in front, this has to come from the first correction. Now, how does this fit with what I said before? Because that's an asymptotic expansion from the wrong side. If you start expanding from q equal to 0, it starts in 0. If you start expanding from infinity, you get an all asymptotic series, which has a term which goes like q to the 0. But then there's something that goes like 1 over q, which would diverge, you see? So one side or the other. I think Joao has a question. Yeah.
Can you explain what is Q now? Because you had n Qs, so...
Yes. Okay, thank you. I didn't want to. No. So the point is the following. There's a very beautiful story of representation theory here. Since in O2, Q identifies a charge and the conjugacy class, you're done. When you are a non-abelian, you have to be very careful about what charge means. Because just the charge, as I defined it here, is not invariant under the action of n. So what you really should be computing is the partition function for fixed representation. So you take your system, you decompose it into representation. Again, in O2 is all the same, but in ON is different. So what this Q actually is the charge of the completely symmetric representation with Q boxes. So this is what I'm looking at. It is an observation that if you just fix the charges as I did, you end up, and you minimize, you end up automatically in the completely symmetric representation with Q boxes, which is that. All the other representations work differently. In particular, the thing that is remarkable, I was surprised that and left us puzzled for a long time, is that if you pick another representation, your ground state is not homogeneous. And that was a big surprise, but I totally didn't want to enter into that here. I mean, there is a lot of structure that comes from the non-abelian story. For the purpose of this talk, I just fixed one charge. If you want to be more precise, I fixed the completely symmetric representation. Okay. Very good. So anyway, was all of this necessary? Why do I need to do large n? Well, one thing that I find extremely nice is the following, that this gives you another prediction, that if you repeat this exercise for O2, O4, O6, O8, then the coefficients that you find on lattice, at least a large n should go like n here, like n thirds, 4n over 3. So is that true? The answer is Well, yeah. In the sense that, of course, this is a computation in large N. You can't study the whole 500 model on the lattice. But you can study the O2, the O4, or 6 or 8, and that's what you find. So what you find, what my friends found, was that repeating this exercise, they found these points here for these coefficients, and these are the curves that you get from large N. So it really looks like the thing works. Okay. But anyway, this is, in a way, all of this is a bit old story. What I mean, finding inspiration from here, what I would like to do is that I would like to stop working around here, which is what I've been doing all the time, and start going along, no? So I hope getting till here. Okay. Now, I will go the other way around in this case. Instead of first showing what to do, fixed charge and finite n, I'll just go directly in large N, and I'll show you how things work. Okay. So the first observation is the following. In large N, you don't need to go to be at the infrared, okay? Why don't you need to be at the infrared? Because your calculation doesn't care. You can repeat all the calculation I did before, keeping finite the coefficients of phi square and the coefficient of phi to the fourth. The fixed point, in order to get the fixed point, before I had to fix R to be the conformal coupling, and U goes to infinity. That's the limit of before. But I don't have to. I can just keep them finite. The only thing that changes is that you remember when I computed the effect, the free energy was a Legendre transform of something. It's this something that changes a little bit. Before it was just a zeta function for which I used the Weil expansion. Now there's an extra term. But really, this is all that changes. This is an exact result at large N. Okay. So, in other words, this little function here, which I call the Gram potential for because thermodynamically that's what it is, actually contains the full large N information about the system. The only thing that remains to be done is to extract this physical information from that function there. I have to specify what is sigma, I computed zeta function, and it's all written there. So how do we extract information from this thing here? Well, let's go the other way around. Let's suppose that our system could be described by an effective action. So, you know, like the thing I did before. Let's suppose I could integrate out the high energy degrees of freedom, and I could write an action for a classical field. Well, in this case, this action here should describe in particular the fixed charge sector. Why not? It contains everything. So what I could do is to study this action at fixed charge. Now, if I do that, it turns out that, think of O2, in any case, it works the same for ON. What happens is that I can do an intermediate step. Instead of studying fixed, just like we did before, remember when we integrated out the dilaton? I can integrate out from here the radial mode of this phi, because it's massive. So how do you do it precisely? What you do is that you take your potential, you write the equation of motion for the absolute value of phi, and then you substitute what you found in the action to get an action that only depends on the other degree of freedom. But look well at the equations you're writing. The equation of motion, it just tells you that mu square is the derivative of v with respect to phi square. And when you put it back from the kinetic term, you get phi square mu square minus, and then minus v from here. But that's a Legendre transform again. So what you find is that if you start from an effective potential, you can reconstruct your Gram potential that before we had constructed from large N with a Legendre transform. Yes.
So there are two limits here involved, large N, large charge. Do they commute?
Okay, so here I'm doing everything in a double scaling limit, large N, large charge, Q over N fixed.
Okay, so that large N analysis you were doing in the previous slide, that was large N only, I saw.
No, it isn't. Okay, I went too fast, but I can show you why immediately. You see, when we fix the charge here, okay, and then we rewrote this action in these terms here. When I'm in large N, I'm just picking the leading end contribution here. But in order for this term to count anything at all, it means that also Q has to be of order n. Otherwise, I can't put it in the same line. So it's intrinsically, all of this is in the limit where Q is of order n. Then Q over n might be big or small, but you are where Q over n is between 1 and n itself. Okay, so that's where I will always be working. The cool thing is that all of this will completely disappear in one slide. So I will not care about charge anymore. The only thing I care about here is that the gram potential I computed before can be obtained as a Legendre transform of an effective potential. But the Legendre transform, at least when it's applied on convex function, is an involution, which means that if the gram potential is the Legendre transform of the effective potential, also the effective potential is the Legendre transform of the gram potential. The gram potential I can compute. It means I can compute the effective potential. The subtlety comes from the fact that I need convexity for this to work. But the effective potential for any theory is always convex. So in this direction, I'm cool. The problem will be, is the gram potential that I compute in large N convex or not? Now, that's a less trivial question. In fact, since I really care about convexity, I don't really want a Legendre transform as I did before, but what I really want is what is called a convex transform, convex dual. So I want to define the effective potential as a supremum of this expression. As long as this equation, the equation that you write in the Legendre transform to define the charge, usually in the Hamiltonian formula, admits a solution, the two definitions are the same. When this equation does not admit a solution, which is when the function is not convex, this gives a different result. And that's all the physics, actually. Let me make an example, okay? Let me consider as an example what happens in 3 dimensions in flat space. In 3 dimensions, flat space, the zeta function is very simple, just mu to the cube. Which means that my grand potential is this thing here. I do a Legendre transform with respect to mu squared, and I get this function here, and that's the Legendre effective potential of the ON model in 3 dimensions. Full stop. In the critical case, when R is equal to 0, this function had been computed a number of years ago, resumming infinite Feynman diagrams. The cool thing of this story is that I get this function direct. This is the resummation of infinite Feynman diagrams without having had to compute a single diagram. I just get the thing direct, bam. Second, I don't need to be at criticality. R is whatever. Third, I'm not telling you the whole story. Because when I define a Legendre transform like this, it's important that when I derive this expression here with respect to mu, I have a solution to the equation that comes out. But if omega prime does not reach 0, it means that there will be points where the maximization condition for this equation here is not satisfied. Now, in the case of R bigger than 0, so when I am in the massive phase, or R equal to 0, which is the critical phase, everything is fine. But when I am in the unbroken phase, where R is smaller than 0, you know, the Mexican hat potential, then what happens is that omega prime does not, you see, this thing does not start flat. It starts already going up. Omega prime never reaches 0. This has a consequence. You see, in the unbroken phase, maybe I confused broken with unbroken before. But anyway, in the unbroken phase, no big deal. The thing in dashed line is the 3-level potential. The red line is the one-loop potential, is the large N potential. They look the same. Okay? Little deviations, but no big deal. In the critical phase, already stuff happens because the 3-level potential is 5 to the 4th. But the one-loop potential that I compute around the origin goes like 5 to the 6th. But this is exactly the 5 to the 6th of before. It's the 5/6 of criticality, the one that we had found with the effective action. In the broken phase, everything is different. Why? Because while the 3-level potential has, goes up and down, that's the that is Mexican hat potential. the effective potential, the supremum definition of the Legendre transform in between here gives a constant. Now, of course, Mattia is saying yes, 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 because he knows Maxwell's rule. This is exactly what you find in thermodynamics. Here, you find it in field theory. So the three-dimensional field theory, just a large N, directly computes explicitly an effective potential that does exactly what it has to do. Okay. Then what is the vacuum here is a different story. We can talk about that later. I see that Matthias is a bit unhappy with time. A more interesting story happens in higher dimensions, because if you're in 5 dimensions instead of 3, there's a crucial difference. The leading term in the ground potential is negative. This means that the ground potential now is not bounded below, and is not convex. Okay, so you see, this is the ground potential. It's convex a little bit, then there's a flex, and then it goes down. The derivative has a maximum, is the flex, which means that when I solve this equation here, until the field has a certain value, it's okay. There are 2 solutions. I have to pick the branch and so on. But when phi is bigger than that value, there's no solution. There's no real solution. The end. If I try to write an effective potential, there are the pillars of Hercules at some point. If I try to push the theory too much, in this case, going towards the ultraviolet, I hit a wall. And there's no theory anymore. The potential becomes infinite, because the supremum of minus a function that is not bounded below is plus infinite. This thing is telling you that in 5 dimensions, the theory is not UV complete. And you just see it just by looking at the convexity of a curve. That's it. What you can do is the following. Remember, I had to solve this condition here, and up here there is no solution. Well, no, there is no real solution. There are complex solutions. So what happens if I put a complex solution instead? Well, it's your choice. Now, what happens is that the pillars of Hercules here that tell you that there is no unitary theory at the back, well, and once I go towards the ultraviolet, now tell you that that point is a branch point. This becomes a Riemann surface, and you get an effective potential that is complex. You can do everything here. You compute conformal dimensions. Conformal dimensions will be complex. This is also a result that was known in the literature, computed in a very different way, but here just comes out directly from here. Okay, so time to wrap up. Here, I've shown you how I can use the I can write large N effective ground potential for finite values of the couplings, and from there derive an effective potential. And depending on how many dimensions I am, I either rediscover Maxwell's rule, or I can find, for example, in 5D that I need a complex CFT to UV complete the theory. All in all, just to close, I hope I convinced you a little bit that with this approach, we have a handle on strongly coupled systems, more or less perturbative handle. And the idea is, again, to pick a sector where you can write a controllable effective field theory. It tends to work very well. Every time we compared it to other things, it actually worked very well. And now we are starting this work to explore beyond the critical point and try to explore really the phase diagram of these theories independently of the large charge, but just using large charge to extract information differently. Okay, thank you.
Thank you very much. We're a little bit running late on time, so we have maybe time for 1 quick questions, or otherwise coffee. Oh.
Can you try to say something about slightly broken global symmetry in the large charge? Like there is a pseudo-non-Gostan boson. So
I don't know. No, I prefer not, because it's too speculative. You can try to see how this breaks the Q3 halves and so on, but because it adds a little mass to the Goldstone, but I don't know anything precise enough to answer a question like this now.
Okay, so what I suggest is that most people interested in discussing more gather around the owl for informal discussions, and the rest of us, or some of us, have coffee, and then we resume here at, I guess, 11:30, or should we? Okay, 11:30. Okay, so let's give another applause to Domenico.